My name is Cory Brown, and we're going to be talking about functional-style JavaScript, practical styles for functional-style JavaScript. Practical, what did I say it was? What's on the thing? Practical functional-style JavaScript patterns. There we go, something like that, patterns. So let's talk quickly about that. Functional style, what does that mean? It's the borrowing of functional programming concepts into multi-paradigm programming languages. So JavaScript is not a functional language. Which is why I said patterns and not, anyway. But nor is it a classical object-oriented language. JavaScript is a prototypical multi-paradigm dynamic scripting language. Wow, that's a lot of words. However, if you've ever read The Good Parts by Douglas Crockford, you know that there is a very elegant language inside of JavaScript that we can find. And there are some really elegant patterns that we can bring out in JavaScript with some care and attention. And that's what we're going to try to do here. So I'm going to show you some code examples. I'm going to talk to you about some principles. Whether you've never really heard of functional programming or any of its principles, or you think you're a fairly expert, actually, if you're a fairly big expert on functional, I'm not going to be able to help you much. I'm not an expert on functional. But I think there's some patterns here that will be useful for any skill level to pull out. We are going to be dealing almost primarily in ES6 and some of the stage, the not quite released spec stuff. So this kind of has an expectation of Babel baked into it, or some kind of precompiler. But these patterns, even if you're not using Babel, they're soon coming to the language, so it's good to be aware of them. And if we ever actually get an internet connection, I can get rid of this red thing at the bottom, but we'll see how that goes. So let's first off, let's get into the functional mindset and what it means to think functionally, because that's really the crux of it. If you can start thinking in these concepts, these patterns will come quite naturally, I think, to you. So first, one of the things, I'm going to be basing this largely on my experience. One of the things I had to do in getting into this mindset is I had to get out of the OOP mindset. And to do that, one of the concepts is to free your data from behavior. And what I mean by that is, unlike object-oriented programming concepts, which intentionally couple data and behavior together, the data, your attributes, and the behavior, your methods, into an object, functional programming concerns itself primarily with behavior, the functions. And it constructs flows that move data through those behaviors. Those two they're completely separate. They are not dependent on each other. So in a typical OOP style, we might have, for instance, a class that has a constructor, and on it has a method which then does stuff to the data inherent to the class, right? So we pass in an away team, and we put that as on a property of the object. The method sendAwayTeam goes through and filters out the red shirt, right? Well, it doesn't filter, it removes it. It removes the red shirt from the away team. Conversely, functional style would approach it a little differently. They wouldn't worry about constructing an object at all. Would say, what do we want to do? What happens here? Well, we're gonna find out who's not gonna die on this away team. That's just finding who's got a red shirt or who doesn't have a red shirt, and letting them pass through. And we're going to be sending an away team which does the filtering. Notice we haven't mentioned anything about data yet. Data hasn't come through here at all. Now, on the OOP side, we're now going to construct this object with a new operator, and now this object has an away team method. If we look at the length, it's got a 5. We call our sendAwayTeam. Now the length of that same object is 4. We've mutated that object. This is pretty typical. On the FP side, we can construct a plain object, a crew object, just out of regular plain old JavaScript object. Then we see that the away team property on that object has size 5. We send the away team, passing it the away team members, and the length is now, still 5? Yeah. In functional programming, we don't like to mutate data, so in order to do that, we're going to create a brand new object that has the crew member filtered out. If any of this syntax looks like really foreign, and you don't know what it is, feel free to stop me anytime. we'll cover most of it. I'll probably talk about it, but if you really can't get past it, by all means, let me know. I'll give you a brief explanation of what's going on here. And there's some links to examples of those actually working. Okay. The next thing we want to do is we want to develop an aversion to state. So what is state? Well, in my personal opinion, state is like a parasitic vine that binds your code to its current use case only, and it immobilizes it. It slowly spreads its twisting tentacles to every part of the application, causing small changes in one part to have cascading effects in other parts of your applications that seemingly were unrelated. To understand one piece of your application and all its effects, you have to understand the application as a whole. And if left unchecked or uncontrolled, state infects your application, making it less resilient, less reliable, less maintainable. So a quick, fun, and useful fact, impure functions, which is what we're talking about here, things that change, that mutate state, increase cognitive load on developers, and it de-optimizes compilers as well. It's a true story. In contrast, though, black-boxed or pure functions, as they're called, are completely portable. They are unbound to your application. They are applicable regardless of the context that they're put into. As long as how you're using it adheres to what it's expecting to get, it doesn't matter where you place them. One only need to understand the function in isolation in order to contribute meaningfully to its maintenance and performance. Its portability makes it easier to test. You're not like mocking out all these other objects that it depends on. Pure functions inoculate those parts of your applications from the infection of unregulated state. I made a point to say unregulated state. State, while you want to have an aversion to it, is also unavoidable, but we need to control it. And that's what these functional principles, hopefully we can do with them, is manage it in a good way. A fun and useful fact, pure functions break less than impure functions. Also a true story. Another way to get into the functional programming mindset is to learn the what and the why of currying. Who does know what currying is? I don't want to feel like I'm shaming anyone. Currying. Can you give a brief definition of it? Shout it out. Go. Somebody had that waiting. That wasn't me. That's amazing. Good job. Currying. Obviously, we're talking about Haskell curry. And it's turning a function that takes multiple arguments into multiple functions that each take a single argument. That's the best definition I've heard, and I think it's pretty succinct. For example, let's take the ubiquitous add function that's always put out there when we talk about currying with functional programming. Add function takes two arguments and adds them together, returns the value there. Is this syntax weird to anyone? Everyone know error functions? Are we good here? OK, good. And we call it like this. We add iron and carbon, and we can get steel. That's great. If we curried it, and watch back up there, we're currying that function. Now we're creating a function that takes argument A, which returns a function which takes argument B, which then returns the sum of that. To call it, instead of passing them into one function call, we make two function calls. We pass in iron, returns a function, we call it again with carbon, and we get steel. When we do that, we can now kind of partially apply arguments to our function. We can create an iron and function, where whatever we pass to the next function is always going to be bound to iron, that first argument, iron and. And if we pass wine in there, now we have Iron and Wine, which is a really terrific band. If you don't know who they are, you should check them out. And we have something this is cool because it's completely different. Here we have steel, here we have music. And we did it with a single definition up here. It's really powerful. This is what currying helps with. So no neat trick, but why would I ever use that? Well, here's a real world example I use almost daily. It's a tap function. Who uses promises? Who finds that in the course of their programming they want to tap into the promise chain? Like what does it resolve to at this point? I don't know. This tap function will help you out there. What it does is a function that accepts a message, then returns a function which will accept the data. That then will console out the message and the data and return the data unmanipulated. We use it this way. If we have some promise, we then over it. We can tap and say, all right, what's the initial resolution? Then it's unchanged, so we do it then, and we do some sort of transformation, something happens. And then we do another tap, and we can find the result of that transformation right there. It's pretty slick. So that's currying. We'll talk a little bit more about currying in a minute. Any hang-ups yet? We good? We happy? Awesome. Yeah. This one? Then, sorry, yeah, is that? Hey, all right. Resolution problems. We good on that? That help? All right, good. So another way we can get into the functional mindset is we think in small generic units of work. Oh, good heavens, time is flying. And generic is a keyword here, so look for abstraction, or look for patterns and abstract those patterns. The curried generic functions can get more specific and specialize down the argument chain. For instance, if we had a function that we want to check the value of a property on an object against some value that we care about, we can have a has property value. We can partially apply that to check against the name on that object we eventually pass in. We check that name to see if that name happens to be Serenity. And once we do that, we can filter out a list of ships to see if the name of that ship is Serenity. Make sense? It's awesome. Composing functions with other functions is another principle that will get us in the functional mindset. Compose, or alternatively pipe, which is just compose backwards. They both effectively accomplish the same things. And a function composition is combining two or more functions to create a single new composite function. Both compose and pipe, which are common names for them, are both function compositions. And just do it in a different order. So for instance, in this case, we're going to pluck a property off of an object. If you're familiar with Lodash, they have this pluck thing. We're going to create a function that maps an object to a property on that object. So say we have an object that happens to have an ID, and we just want to get those IDs out. We can map over and just produce the IDs, an array of IDs. We're going to dedupe a list of primitives, so not objects, but their primitive values, strings, numbers, that sort of thing. We want to reinflate properties from our source, and when we have these functions in hand, we can produce a function by using these together called dedupe by. We're going to take a list of objects and dedupe by a property on that object. Make sense? We pass in some property. Now we have to partially apply our reinflate by prop from source function. We're going to pass in the property we care about. This returns our values here. So we're going to compose the reinflate prop from source, passing it the list we have. We're going to dedupe our primitives, and then we're going to map to, well, sorry, it goes this way. We're going to map to some property that we passed in, dedupe them, and then reinflate to their objects, their original objects. If you want to see that work, that's right there. We don't have time because time goes by really fast and we have really short time. But do you see how you can compose functions together to produce a single function which does more complicated things than those simple ones? These smaller ones can be tested very, very precisely because they do one thing and only one thing. And then once we're quite certain that these functions work exactly as we expect them, we can combine them and we don't have to worry so much about testing this larger one, this dedupe by, because each individual piece has been adequately tested. Lots of libraries come with a compose helper, such as Lodash _ Redux has its own Lambda, but it's also really easy to roll your own. This is compose, guys. That's it. That's how you compose functions. It's really rad. Or if you prefer, pipe. So compose uses a reduce write, pipe uses reduce. That's it. Pretty slick. So let's talk quickly about higher order functions, which we've seen a lot of already, actually, in the course of this. Higher order functions are any functions which accept functions as an argument or return functions. So I know I'm going really fast. If I'm going too fast, please stop me. I'd rather you guys learn a few of these things rather than us barrel through and nobody learns anything. So here we have an example of a map function which takes a mapping function and a list of things and then maps over it. It's a higher order function because it accepts a function as an argument. Another case, we have a get value of function. It accepts a property name and returns a function that expects an object. This is a higher order function because its return value is a function. Both of these are higher order functions. So higher order function tip number 1, I would recommend that you arrow function or lambda all the things. And I know if you guys followed some of the leaders in our community, some smarter people than I have said that arrow functions aren't for every scenario. I have yet to find a case where that's really true, actually. And that might be just because I look for opportunities to use these arrow functions rather than not. I avoid scenarios that would require me not to use them. And I found actually I tend to write better code when I do that. Maybe that's just me. I don't know. Arrow functions are particularly beneficial for returning other functions. It demonstrates visually the successive flow of them. So if you look, the second example over here, the get value of, is a function that takes prop name, which turns a function, which takes object. And that arrow just shows, it goes this way, guys. I think it reads very nicely. If you're unfamiliar with the arrow function syntax, it can look foreign and strange. But once you wrap your head around the syntax, reading that is phenomenal, I think. It also makes currying fun and easy. So higher order function tip number 2 is write only singularity functions. What do I mean by singularity functions? The number of arguments that a function takes. 1 argument. Do this at least until you're very comfortable with the idea of currying and what its value is, where you should use it. Let's take an example of making a request. Let's say you need to make a request and pass an API key, and you have to pass a user. You want to make sure the API key is valid. You want to make sure the user is authenticated. And then you want to go to some URL, right? You might write a very simplistic function this way. If the app key is valid, and if the user is authorized, then make the request. Otherwise, we're going to return a 401. How would you curry this? Well, it's actually very, very simple. Do you see that? Look at the top line. Doot, 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 doot. That's the difference between a curried function and a non-curried function. And the arrow functions really make that a one-liner. Without the arrow functions, you got all kinds of things going on. It's very, very nice. So now we have a make request is a function that takes an app key, which returns a function which accepts a user, which returns a function which accepts a URL, which finally makes a request. We use it this way. Let's say we want to make a request, and we always want to make a request with the app key of empire.gov. And then as we get in there, we have a request from the user, so we want to bind the next step to the user. So we make our app request as user Lord Vader. Now every request we use with that function will be bound to empire.gov and Lord Vader. And finally, we can make the request to get the plans for the Death Star. Cool? Bueno.
So are these all singletons, all these users and functions and stuff? So I use it again elsewhere in the application when your values kind of get known.
No. So if you use everywhere you use make app request, no matter where in your application you use it, it will be bound to this app key forever. Everywhere you use this function, it will be bound to Lord Vader forever. If you want different app keys, different users, you use the upper one, the make request. You want to create a new function that's bound to a different value. Right. So you would probably make the make app request at app startup because you have the app key and you're going to bind to that app key. You wouldn't make the one that's bound to the user until you're inside of the request flow. Then you would make that, and every subsequent request you have to make to some API to get the information you need to respond would be done on behalf of that user, but only after you've entered into that route that, yeah. Once you have the information available to you to bind, then you bind. OK, so any other questions? Let's talk about the Tau of blackboxing. Oh my goodness. OK, so little time. A black box is a device or system or object which can be viewed in terms of its inputs and outputs without any knowledge of its internal workings. Its implementation is opaque or black. That's according to Wikipedia. Thank you, Wikipedia. A black box is pure in a functional sense. And to define what that means, functional purity is a principle of functional programming that, given the same input, will always return the same output, and it does not have any observable side effects. So you can't examine something, you can't see something happen outside of that function. A side effect is a change of system state or observable interaction with the outside world that occurs during the calculation of events, okay? So, you want to strive for pure functions. To give you an idea, some signs of impurity are implicit dependencies. You guys see the implicit dependency here? It is the base64 module. We can solve that by making, with not necessarily our function pure, but this module itself pure by explicitly importing base64. So black box tip number 1, make all dependencies explicit. Either import dependencies into a single responsibility module or pass them to your single responsibility function, but single responsibility is key there. External assignment is another example of impurity or sign of impurity. Here we have all kinds of variables that are getting mutated, changing, that are being assigned from outside of the core of what's happening. We can simplify that quite a bit by using some of the array methods that give us it's an abstraction over these looping techniques. Black box tip number 1, initializing or reassigning variables is a smell. If you find yourself saying let var, and then later on assigning to or let some variable, later on assigning to that, that's a smell. Something's not quite right there. It's a sign of an external dependency. And if you need it, then what you should do is pass it around like a bad white elephant gift. It goes, it goes wherever it needs to go. Mutated arguments, another example of impurity. In this case, we have an object we're passing to. We want to add a team member to a team. We're going to pass in the argument or the object, and we actually mutate that object with the new member of that team. And this is something that we generally want to frown upon. What we can do instead is create an entirely new object with the object spread operator. Who's familiar with the object spread? Who's not familiar with the object spread? Okay. If you are familiar with array spread, which is in the new JavaScript language, ES6, it's very similar in principle, used almost identically, except with an object instead of an array. It's very cool. Black box tip number 3, we're going to look at immutables tip number 3. We'll get there. I hope we'll get there. Another sign of impurity is referential opacity, or you've probably heard of referential transparency, which means it's exactly the definition of black box. If you pass in an argument, a certain set of arguments, you always get the same result. It's, I'm forgetting the words. You always get the same result when you pass the same arguments in. So if you have an example of, here, a random number generator, problem with that is you actually can't avoid that. It's always going to be different. That's kind of the point, right? So sometimes it's not avoidable. What you want to do, though, is push impurities out to the edges of your application. That means when you do network requests or write to disk or render to screen, these are the edges of your application. That's where you want to manage your state, manage your impurity at those edges. Oh my goodness heavens. Eric Elliott has a nice thing about that too. The power of immutables. I'm just going to skip to the. I'm virtually out of time. Certain things are immutable in JavaScript: numbers, strings, symbols, booleans, null, undefined. These cannot change. However, objects are immutable. Objects, arrays, functions. You can change them. You can add things to them. You can mutate them. Why favor immutability? Because of state, or rather lack of state. In fact, a very wise person once said a reliance on external state is one of the most common scenarios of unintended side effects. That's me. Immutable data structures require the creation of new context for every new value, and this prevents one from inadvertently affecting shared state. Am I over time, or do I have like 2 minutes? Okay. Let's get to step number 3, because that's an important one. And then we'll be done. Also, I talk about freeze and deep freeze. I highly recommend that you learn object spread, because it will change the way you write, and it'll make it more mutation-free. The freeze and deep freeze, my advice is you probably don't need them, actually. Finally, a word on inefficiencies. You may have heard that functional programming is less efficient than object-oriented, or rather, the fact is, to today's JavaScript engines, that's just not really, it doesn't matter. Any difference in there is kind of irrelevant. I'm sorry it was so rushed. There's actually a lot of stuff in here. I do have the slides on slides.com under Cory Brown Functional-style JS. You can go on there and look at them all on there. It's fun stuff. If you have any questions, I'm happy to take them out in the hall. I like talking about this stuff. Thank you guys. Again, sorry it's so rushed.